planets, took the famous blue marble image of the Earth, and it really paints, I think, just an incredible picture of our home planet and how lucky and precious planet Earth is, especially when you compare it to the amazing views we've recently gotten from the Dawn spacecraft, which is a somewhat Ceres hostile world, dwarf planet Ceres. We've just announced yesterday a Kepler discovery of a sort of a parallel, a cousin solar system to that of our own solar system, with a G-type star much like our sun, a little bit older, and an exoplanet that's about 60% bigger diameter than the Earth, right in the middle of the habitable zone. It's truly amazing the things that we're doing, but the images that we've been getting and the science we've been getting from Pluto is really just been more than amazing, and privily a scientific theory that science never sleeps. And if you look at our panel here, they actually look pretty cheery for a group of scientists that have not been sleeping for the last few weeks. But they are here to tell us about the most recent amazing results from the Pluto New Horizons mission. And I'm just thrilled to be here to hear those results.
Okay, so we have, before I introduce our panelists for this afternoon, obviously the NASA account, social media buzz with this mission and the results and the images. Follow the NASA accounts on Twitter, YouTube, Facebook, and other NASA accounts. And send in your questions at hashtag #AskNASA. And a lot of questions are coming in. We'll try to answer those as quickly as possible, but keep them coming in. And you can follow the conversation, and there's still a lot of conversation all over the world on this historic mission at hashtag Pluto Flyby. And again, online, all of the information today and in the future can be obtained by going to www.nasa.gov/New Horizons. First up, you will hear from Jim Green, Director of Planetary Science at NASA headquarters. Alan Stern, New Horizons Principal Investigator at Southwest Research Institute in Boulder, Colorado. Michael Summers, New Horizons Co-Investigator at George Mason University, Fairfax, Virginia. Kathy Olkin, New Horizons Deputy Project Scientist, also at the Southwest Research Institute. And William McKinnon, New Horizons Co-Investigator at Washington University in St. Louis. And with that, I'll turn it over to Jim.
Thank you very much, Dwayne. July 14th was very historic for NASA with our very successful flyby of the New Horizons spacecraft through the Pluto system. And we're just 10 days from that, and yet we've only had about an opportunity to see about 5% of the data. As many know, we stored that data on board as we flew through the system, and it's just now starting to come back. Each and every day, the science team has been huddled, looking at the data as it comes back, and is always surprised. And it's just quite a pleasure to be part of that team, to look at the data when it comes in and see the new discoveries that are coming out. Now today we're going to talk about some of that latest data that came in within the last few days. This is a spectacular set of data, but it's also data that happened and was taken on board, stored prior to the encounter, and it's post-encounter, after the spacecraft had an opportunity to fly through the Pluto system and look back to Pluto as it's hurtling away at more than 16 kilometers per second. These are just amazing discoveries. And so without further ado, let me turn it over to the principal investigator, Alan Stern, to start it off. Alan?
Thank you, Jim. Well, as Jim said, last week, the United States, through our project and NASA, explored the farthest frontier ever explored by humankind, the Pluto system. And we can't tell you how happy we are just to be back as a team and to tell you what we've been discovering. We came back last Friday and gave a first report about just the first couple days of data download and the first reactions that we had to it. Now we're 10 days out, 7.5 million miles from Pluto. We've had more time to think about the data sets that are on the ground, and equally importantly, we have about 3 times as much data on the ground. Now, that, as Jim said, it's not very much of the total data load. We have about 4 to 5% of the data back. 95 or 96% of it is still on the spacecraft, so we're only scratching the surface, and we've got some great discoveries to tell you about. We also want to tell you that besides the data sets, there's one other way on this project to know that we've really done the exploration. We're on the other side of Pluto, and that's this bumper sticker that's inspired by Val Malder, our deputy systems engineer. It says, "My other vehicle explored Pluto." It's got a nice picture of Pluto made by New Horizons in the rearview mirror. That's how you know. Well, I want to say a few things, and I'd like to call up my first graphic, which is just a hauntingly beautiful image of the double planet system, Pluto-Charon, with Pluto on the left and Charon on the right. This was made a few days out on approach with true color added from our Ralph instrument on top of a LORRI image. And as I tell you a little bit about where we are in the mission, just feast your eyes on this. We've never been to a double planet system before, and it's turning out to just really be a scientific wonderland. We've now finished the first phase of downlink. That was an intensive 10-day period in which we sent down images and spectra and other data sets just to whet our appetites and tell us the basics about the Pluto system and the discoveries that you'll be hearing about by myself and Mike, Kathy, and Bill report on some of the most important findings that we've already made in these few days. We're now moving into a second phase of downlink that's a little bit different, and I think it's important that everyone understand that difference. We'll be transmitting home now a lot of engineering data from the flyby, as well as data from our plasma, our in situ instruments, our student dust counter, and header data to go with the images and spectra that we've already got. And so for the next couple of months, until we reach mid-September, it'll only be occasionally that we'll have new images on the ground and available to release. But starting in September, the spigot opens again. And then for about a year, maybe a little bit more, the sky will be raining presents with data from the Pluto system. It's going to be quite a ride. We're really happy about the amount of interest in this mission. As a mission team, we're excited to share it with all of you. And we're going to do some of that right now. We're going to get right into the science. For some of you, if you're seeing a cardiologist, you may want to leave the room. There are some pretty mind-blowing discoveries that we're going to talk about. And if I can have my second graphic, I want to show our 2x2 mosaic of the Pluto system. This has twice the resolution of the previous best global image of the approach hemisphere. And really, it's just mouth-watering. The level of detail is spectacular. This image has a resolution of about 2.2 kilometers per pixel. And I think just looking at it, you can tell, as our science team can, that Pluto has a very complicated story to tell. Pluto has a very interesting history, and there is a lot of work that we need to do to understand this very complicated place. I want to stress that. I want to drive it home by showing you this image at higher magnification. So if I can go to the next time step, we're going to look at just the northern half of that image. And we could easily blow it up even further. And you can see across the northern terrains here, which include the North Pole, by the way, and this is a true color image, essentially true color as your eye might see it, a whole range of geologic expression. Kathy and Bill will be talking about this quite a bit more, so I won't steal their thunder, but just let your eyes gaze from the left on the western limb across the disk over to the east, and you can see different geological units, kinds of features. It's telling that complicated story again, which is there for us to unravel. And if I can have the next time step and we can go to the south, you see a still more complicated story with the great equatorial dark regions, with Tombaugh Regio, as we informally call it, the heart on Pluto, and what look like massive tectonic features, both radially emanating from Tombaugh Regio as well as others that run more or less north-south. You'll hear more about that later. I do want to tell you about one aspect of the interpretation that we've been making over the last week in looking more carefully at the imagery of Tombau Regio, or the heart. Like a real heart, it has two lobes on the left and on the right side. The left is the western side, and I think even to your eye you can distinguish a difference between those two. The right lobe looks like a much thinner deposit that's been painted on top of the topography. And our interpretation of that material in the right lobe, as well as the material emanating to the south below the western lobe, is that in both cases we believe the source for that material is the western lobe, that its material is being, bright material, probably nitrogen snow, is being transported off the source region of the western lobe, but perhaps by winds and aeolian transport, perhaps by sublimation and winds and then recondensation, or perhaps by a process we haven't thought about. But in any case, we think that we're coming to understand this feature just a little bit. It is early days. Bill may have a little bit more to say about that. What I want to talk about next is our next time step, which is a false color image, which has really been stretched to show the dramatic differences in color units on Pluto and how they correlate with the geology. This is pretty mind-blowing. Kathy's going to have a lot more to say about it and what it means in the bigger picture. But as you can see, for example, Tombau Regio with the western and eastern lobes that I was just talking about have different colors. They're telling us something in that. And soon we'll have composition spectroscopy to support that at very high resolution. You can see that the polar regions have a different color still, and that as we get down into the dark equatorial regions, there's still more information. The geology and the color, probably the composition, seem to be correlated. And this tells us that the payload that we brought to bear on the reconnaissance of the Pluto system was really the right payload. Because we have on board the spacecraft now tremendous data sets with higher resolution color than this, higher resolution panchromatic mapping for doing the geology, and a spectacular data set with compositional information with over 64,000 pixels that we put on the surface to get a spectrum at every location. We're going to be able to tell this story very well over the next year. Really looking forward to that. I'm going to move on to the next time step, tell you a little bit about atmospheric science, where we've also made some advances. This particular view graph is to illustrate something about our ultraviolet occultation of Pluto's large moon, Charon. This was an experiment that we designed years ago to look for an atmosphere around Pluto's largest moon. And there's been a pretty big body of literature speculating about how Charon could have an atmosphere. We just got the summary data down in the last few days. We don't yet have the full spectral data set. In fact, we won't have that data until September. But if you look at that time step, you'll be able to see the little yellow line represents the path of the sun as seen by from the spacecraft moving behind Charon. And you see it just clips the northern regions of the moon. That's exactly what we plan. That's exactly how we plan this trajectory to go. And just as you clip on either side of the body, you can see in that red and white graph that the light level from the sun just plummets straight to zero. Doesn't look anything like the solar occultation data that we showed you last week for Pluto, where we could clearly see a refractive signature, a slow decline in the light levels. Here, it's just basically a square wave, telling us that Charon has much less atmosphere than Pluto, if any. We really can't put strict bounds on it yet because we don't have the spectra. But as I said, we'll be able to do that when we get out to September because those spectra will be downlinked. For now, all that we can say is it's a much more rarefied atmosphere, and that confirms our pre-flight notions, our pre-encounter notions. And we're really looking forward to seeing just how rarefied that is. It may be that there's a thin nitrogen layer in the atmosphere, or methane, or some other constituent, but it must be very tenuous compared to Pluto. Again, emphasizing just how different these two objects are, despite their close association in space. I want to also speak to another part of our atmospheric science, which is the fact that we've now got to the ground some of the radio occultation data for Pluto, where the Deep Space Network transmitted a powerful signal up to Pluto timed to arrive just as the spacecraft was passing behind the planet so that we could measure the refractive index of the atmosphere. And as you'll hear more from Mike, we got it. We got the data. They're beautiful data. And they have a wonderful scientific surprise. The pressure in Pluto's atmosphere, measured for the first time in history, is lower, substantially lower than predicted. And that's probably telling us a story, and Mike will have more to say about that. I'd like to close with one more time step. This is really a spectacular image. This is a silhouette of Pluto looking back after the flyby. I think this is just fantastic. This is our equivalent on New Horizons of the Apollo Earthrise photograph that proved we were there. You can only get this image by going to Pluto and crossing to the far side and looking back. Now, as striking and spectacular as this image is emotionally, it also represents a huge scientific discovery, because you see above the dark disk of Pluto a band of light, which is actually telling us that Pluto has a haze layer in its atmosphere, and Mike's going to tell you more about it.
Okay, thank you, Alan. Good afternoon, everyone. I'm going to new results on the atmosphere that are basically changing the way we think about Pluto's atmosphere. We're having to start from scratch to understand what we thought we knew about the atmosphere, the way the weather worked and the way the climate and the evolution worked. So we're going to have the first time step, please. The first graphic, please. Okay, this is one of our first images of Pluto's atmosphere. Now, this was the image that stunned the encounter team. For 25 years, we've known that Pluto has an atmosphere, but it's been known by numbers. This is our first picture. This is the first time we've really seen it. This was the image that almost brought tears to the eyes of the atmospheric scientists on the team. Could I have the next step, please? Okay, now what I want to tell you now is that what you're seeing here. This is the atmosphere backlit by the sun, and the light, the crescent that you're seeing, is light, sunlight, scattered by small particles in the atmosphere. And these particles constitute a haze layer. Now, the inset is a cross-section of that haze layer, showing structure. The colors have been enhanced. They're not real colors, just so that you can see that there is structure. There is structure. There's an argument going on in the team whether this is dynamics or chemistry. It's probably both, but the real answer is that this is our first peek at weather in Pluto's atmosphere. Okay, could I have the next time step, just to illustrate that a little bit more? There's a hint that there is either a layer of haze at 30 miles, 50 miles, or a combination of layers and waves in this region. Those are the kind of things we're going to have to sort out over the coming weeks, and that's going to tell us about the details of how the atmosphere actually works. But the haze is extensive. It extends at least 100 miles above the surface. That is a big surprise. That's 5 times further than our models predicted. Models predicted that haze particles would form low in the atmosphere where the temperatures are cold, but it's forming high in the atmosphere where the temperatures are hot, or at least hot from Pluto's perspective, which is not hot from our perspective. But nonetheless, it's a mystery. That's one of the things that we're going to have to sort out in the coming days. Okay, the haze is pretty. It's a way to see the atmosphere, but it's a piece of a big story that we're trying to understand from Pluto. And that is how the atmosphere and the surfaces are connected. So I have a simple animation to illustrate one aspect of that connection. Could I have the next time step, please? Okay, this shows how methane in the upper is broken apart by ultraviolet radiation from the sun into chemical components, radicals and small atoms and molecules that react, trigger a set of chemical reactions that form complex hydrocarbons, like ethylene and acetylene, which were detected by New Horizons. As time goes on, these build up, they saturated, and they should nucleate to form haze particles, which then grow, and eventually they will get big enough so that you'll see a haze layer and they will fall to the ground. At some point in this cycle, those haze particles are chemically processed to produce what we call tholins, which are chemically altered hydrocarbons that have a red color. And we think that that is how Pluto's surface got its reddish hue. And in a minute, Kathy's going to talk more about the color and the composition of the surface. But this is just one piece of that story. It's not a coherent piece yet. There are some mysteries. As I said, we don't understand why there's a haze layer at up to 100 miles altitude. It really is a mystery. Okay, the next story regards surface pressure, and I'll just give you a little bit of context here. In a planetary atmosphere, the surface pressure at any level is a measure of the weight of the air above that level. And weight is gravity acting on mass. So if you know the surface pressure of a planet's atmosphere, you can get a pretty good estimate of the total mass of that atmosphere. And it's important because that's a way of quantifying the global state of an atmosphere. Okay, so I can have a next plot, the next graphic, please. Okay, this shows surface pressure on Pluto as a function of time. Now, the units might be a little bit strange to you. They're in microbars. A microbar is 1/1,000,000th sea level pressure on Earth. And the time scale there is from 1989 before the present. Now, what is interesting here is that in 1989, Pluto was at its closest distance to the Sun. And now Pluto is moving away from the Sun in its very elliptical orbit. As it moves away, it should be cooling. The nitrogen should be condensing onto the surface, and the mass should be decreasing. But we don't see that. We see the exact opposite. That has been very interesting, nonetheless. We have been trying to figure this out. Well, what I'm going to show you now is a new data point, some more information that we have to add to this story. It is just one data point, but I do want to say it is significant, and we are going to have to figure it out. Okay, so this is it. This is what REX, the radio science experiment, has contributed to this story. A new data point which shows that the surface pressure is at most 10 microbars. That's an upper limit. So the mass, if you will, of Pluto's atmosphere has changed by a factor of 2. It's decreased by a factor of 2 in about 2 years. That's pretty astonishing, at least to an atmospheric scientist. And so that's telling you something is happening. Now, it is just one data point. These are early retrievals. We've got more data coming, as Alan says, and there's more to the story. But it's another mystery that we're going to have to deal with over the next few weeks, months, years, and so on. Okay, and now I'm going to turn it over to Kathy Olkin, who's going to talk about the color and composition of Pluto's surface.
Thanks, Mike. So I'm going to tell you about the color and composition and try and tie this together so that you can understand what we know from this color. The color is really an indicator of different surface compositional units. So if I could have the first time step. This is that same false color image that Alan showed, and I'm going to talk through it and tell you what we're seeing scientifically and some of the things that we know and we understand from looking at this image. So first of all, you can see the dark region down at the bottom of the image. That's near the equator, and that's the darkest region. And as you remember, there's dark regions all around that area, even on the other side of Pluto. And then just above it, it's a little bit brighter and a little less red. And then at the North Pole, you see the brighter ices. So if I could have the next time step, putting this latitude and longitude grid on the image allows you to help draw your eye to that banding pattern. Now I want to talk a little bit about it because it goes to the complexity that Mike was just talking about the atmosphere and the surface and the interaction. Pluto has a very complicated seasonal pattern of transport of ices. It takes 248 years for Pluto to go around the sun. And Pluto has a very eccentric orbit. So sometimes it's much closer to the sun than at other times. Also, additionally, Pluto's North Pole is tilted over at an angle of about 120 degrees relative to the plane that it orbits in. All of these factors together cause us different parts to get different amounts of sunlight. And the sunlight is powering the sublimation of the ices from the surface into the atmosphere. And so some parts are kind of baked, like near the equator, and other parts receive these condensation of these ices, as you can see on the North Pole here. And so we've got a differing pattern that you can see manifested on Pluto that we understand from modeling of the seasonal transport of these ices. But there's one glaring difference in this pattern that I just called out, and that is Tombaugh Regio. Next time step, please. Tombaugh Regio clearly interrupts this pattern of latitudinal variation of colors and brightnesses. And one thing I should add is that those darker regions in the story I was telling of